Thank you very much. I'll just take a second while the slides are coming up to acknowledge my co-authors, Brian Wow and Reg Beer from Lawrence Livermore National Laboratory, Jen Heldman and John Stock from NASA Ames Research Center. Okay, I'm an early career postdoctoral research geophysicist, so I wanted to kind of introduce myself here quick to the community because this is the first talk I've been given, will be giving after changing disciplines almost. So I come from the resource exploration side, or resource prospecting, as Clive would say. So I have a joint USGS NASA postdoctoral research project looking at applying terrestrial geophysical techniques for off-road resource exploration. And these terrestrial geophysical techniques could be things like seismic arrays or ground-penetrating radar, which this talk will be about. So this research project explores the feasibility of applying near-surface geophysical techniques to map the shallow subsurface of planetary bodies, improving our ability to detect, characterize, and map in situ resource occurrences. So for the purposes of this talk, I'll be looking at ground-penetrating radar in the upper meters of the moon and looking for water ice and volatiles. Where were these measurements taken? So I'll be showing some preliminary data at the end of this talk, and these measurements were gathered at the CERVI Lunar Regolith Lab at NASA Ames. CERVI has managed 2 shallow lunar regolith testbeds where they were previously used for the Viper mission research as well as community outreach activities. One thing you'll notice here is that they're shallow, and if we're going to be trying to run geophysical surveys in shallow testbeds, this might not be the best place to do this. So I lobbied and wrote a proposal to build a deep testbed with some of the regolith that we had left over there. And as you can see, I was successful in that endeavor. So I built a 2 meter by 4 meter by roughly about 1 meter deep test bed holding about 10 metric tons of crushed anorthosite or lunar regolith simulant with some basaltic glass in there as well that we could start to run some preliminary geophysical experiments with. So the idea behind this was that we had a walk-in freezer at Ames where I could mix up samples of regolith with ice, have them prepared, and then bring them to the test bed and quickly set up and run these geophysical surveys with ice in place and get some experimental data that we could then use. Obviously, this is a low fidelity type of setting, but then we could use to maybe excite the community and get some more interest in these sort of techniques and funding to move some of these projects forward. The different mixtures that I looked at were 20% all the way down to 2.5 weight% of water ice mixed in with the regolith. And the samples that I'll be kind of showing are these blocky ones that we placed within the test bed. So roughly 30 centimeters by 25 centimeters by 12 centimeters, or a 12 kilogram sample. Now for the star of the show, this is the multi-static ultra-wideband ground penetrating radar system developed by Lawrence Livermore National Laboratories. This is a lightweight, so 2 kilograms, and low power, so around 15 watts right now, multi-static radar system. This was used for a variety of Department of Defense applications. You could think of maybe finding things that go boom within the subsurface. Lawrence Livermore was able to integrate these on drones as well as autonomous utility terrain vehicles, which you can see here. And I got a tour of their lab and saw the capability of this system for detecting things in the shallow subsurface and thought, hey, would you guys like to try this out in the test bed? This looks like it's one of the more advanced radar systems I've come across in terms of exploration geophysics. Let's see what it can do. So the idea here was then to repurpose kind of an existing system with this idea of profiling for volatiles in the shallow subsurface. So how the system works and how it's unique is it has an array of waveguides array of transceivers. So this is the multi-static component to it. So if you have a monostatic radar receiver, it's just one transmitter and receiver that acts, pulses, and then will respond after that and listen to that pulse that comes back. You could have bistatic ones that are a pair, a transmitter receiver pair. And where this is different is you have this geometric array of them. So you'll pulse along one and then listen along all the others. So you get spatial information along the length of the array. And of course, if you move this array forward into the screen, you can get a synthetic aperture stitching of that radar and get a 3D image within the subsurface. So these are time signatures on the order of nanoseconds, and will pulse through these different channels, building up this array as you move forward. Where it's also really quite unique is it has an ultra wideband capability. So I am kind of visualizing this with the spectrum of colors within the band, but instead of just pulsing on one frequency, such as 200 megahertz, it can pulse across a wide frequency band in near real time. So what this sort of radar signature would look like for a 2D array, or just one of these waveguides, this would be, your typical radargram. If you combine all of them using a tomographic reconstruction algorithm, you can start to look at actually being able to locate the volumetric area of what you're looking at within the subsurface, handy for finding things. And what this really gives you the power is if you have a test bed shape, 4 meters by 2 meters by 1 meter, you can map out the volume of this down to roughly centimeters scale resolution, which is quite unique for radar systems. So jumping into the results and thinking about this radar voxel that I was showing, the projection of it. So the data is going to be on the left-hand side here, and then these kind of images to help orient yourself as to what you're looking at. We have the top image here would be a down-looking view onto the test bed. And here you can see where the radar was able to detect where this block of ice was put in. Obviously, we use blocks as kind of this preliminary approach to begin with, because this is what this radar system was calibrated to kind of look for, was shapes within the subsurface. But you can imagine moving forward, we're going to be looking at more kind of examples that would be representative of what could be in the subsurface on the moon. So this was for a 10 weight percent Regulus ice mixture. And then this is an example of what we were able to do with the 5%. Now, the challenge here is we're getting close to the noise floor of the radar system. You can see quite a lot of clutter where it's getting a little more challenging. And if we didn't know that we had put this ice block here, we might not be able to make that distinct detection. There's a lot of processing that had to go on to be able to pick this up. But it's still really encouraging kind of initial results to see where this could go moving forward.
1 minute left.
Thank you. So one other thing I just wanted to show is kind of flair for what the system could do. We had a metal NASA worm logo built, and I buried it within the test bed. And then on the right-hand side here, this is again a top-down image of what the sensor can kind of resolve within the test bed. So you can see roughly where this was picked out. And then kind of a video looking down through the data, so kind of taking a flat layer and going down. And if anyone is familiar with ground penetrating radar data, this is quite remarkable that you can actually read something with ground penetrating radar data. So this is really impressive to me anyway, as someone coming from the industry that's used to looking at little squiggles and things like that and trying to make interpretations. So very exciting stuff overall. So future work and development that we've been looking at, Lawrence Livermore, as well as NASA Ames, has expressed interest in kind of developing this further and having a collaboration. So we are looking at, the space enabled version of this would be what we call SLIVER, which is the subsurface localized investigation of volatiles with radar. We'd be looking at doing things like extending the operating depth, decreasing the antenna size, weight, and average power consumption, conducting basic thermal testing, environmental testing to raise the TRL, as well as conducting further laboratory tests within the dirt test bed to be able to look at other volatile species, such as if it could detect CO2 and determine whether or not there's a difference in the spectra between that and water ice. So with the final slide, I just wanted to give a big thanks to Survey. None of this would be possible without the test bed, and particularly the collegial nature of Joe Manofra there, who really helped me. So thank you very much.